So we've been adding and subtracting polynomials, and they've all had integer coefficients. So that means either a positive whole number, a negative whole number, or zero. So we didn't have to work with fractions or decimals or radicals at all so far. But those are numbers you've been working with for years, so you should know how to add them and subtract them, but we're going to look at them anyway. So as a reminder, what is a rational number? A rational number is a number that can be written as a fraction or a ratio. So here are a couple rational numbers. This. The simplest would be any number, 3, and the reason for that is 3 is the same thing as 3 over 1, which means it can be written as a fraction. Another example, 0. 0 is 0 over anything except for 0. 0 over 1, I suppose. 2/3 is a fraction, as it's written as a fraction. We have 4/5. 1 1/3, because that's the same thing as 4 over 3, so that's a fraction. So as long as these are fractions, these are all rational numbers. Okay, here's one that might not stand out to you. Any repeating decimal is actually also a rational number. So 0.333 is equal to, that repeats forever, is equal to 1/3. Therefore, 0.33333 is a rational number, as are all repeating decimals, and all repeating decimals can be written as fractions. And if there's time left at the end of this video, I'm actually going to show you how to do that. And it's one of the things I found most interesting that you can do with algebra. So these are rational numbers, and irrational numbers are numbers that can't be written as a fraction or as a ratio. And the most famous is pi, which is a non-repeating decimal. It's 3.14, and it never repeats a pattern anywhere, so there's no way to make it into a fraction, which is what we do with repeating decimals. A repeating decimal will at some point allow us to make it into a fraction because of its repetition. Another one is e, which is called Euler's number, which is 2.7 something, but it's a repeating, it's a non-repeating decimal also. The ones that we are commonly accustomed to are radical 2, radical 3, radical 5. There's infinite amount of radicals that would work as irrational numbers, and we can't add rational numbers to irrational. We can't really add rational numbers to irrational numbers, with the exception of 0, because you can add 0 to anything. But you can combine certain irrational numbers, which we're going to look at also. But you do need to remember how to simplify both fractions and radicals. So looking at a simple fraction to simplify, if we had 4 over 8, we can simplify that to an equivalent fraction by dividing the top and bottom by the same number, or multiplying the top and bottom by the same number. Let's actually do that. Let's multiply the top and bottom by the same number. So if we multiply the top here by 2 and the bottom by 2, and the reason you're allowed to do that is 2 over 2 is 1, so I'm multiplying by 1, and you can multiply anything by 1, it doesn't change its value. So that's actually equal to 8 over 16, which is also a half. And same way we multiply them, we can divide them both by 2. So rather than doing that way, we can divide the top and bottom by 2. You know, 2 goes in here twice, and 2 goes in here 4 times. That will give us 2 over 4. Okay, and we could say 2 goes in here once, and 2 goes in here twice, and that leaves us with 1/2. So you can simplify fractions or make them more complicated by either dividing the top and bottom by something or multiplying the top and bottom by something. Radicals. Simplifying a radical is a little confusing. When you're simplifying a radical, what you're really doing is making the radicand less complicated. So let's say we had radical 75. It has a factor that can actually be has a square root, because 75, if you take the square root of 75, you actually get an irrational number, a never-ending decimal, a non-repeating decimal. So this is the same thing as saying radical 25 times radical 3, and we know radical 25, the square root of radical 25 is 5. So this is 5 radical 3, which is much simpler, but still irrational, because this piece is irrational, so it's still irrational. Alright, let's take a look at adding some of these numbers. So subtracting two fractions, as you probably remember, you can only add or subtract fractions when they have like denominators. You can multiply or divide them if they don't, but we'll talk about that another time. And just like before, we can change these by either multiplying the top and bottom of a fraction by something in order to change it, or dividing them, and we need to make these have the same denominator. So my thoughts would be to multiply the bottom of this one by 5 and the bottom of this one by 2, and that way they'll both have denominators of 10. So it's always easy to multiply them by each other's denominator. So let's multiply this one, the top and bottom of this fraction, by 5, and that'll give us 15 over 10 minus, multiply the top and bottom of, let me undo that, multiply the top and bottom of this fraction by 2, and we'll get 12 over 10. So this is like having 15 slices of a 10-slice pizza, and you take away 12 of them, you now have 3 slices of a 10-slice pizza. Or what I prefer to do when I write this way is say 15 minus 12 over 10. So you can write them over a common denominator, and then we get 3 over 10. Okay? This one's the same idea. We're going to multiply the top and bottom by the same thing. I'll do this in green so it doesn't blend. I like to write the fraction in parentheses when I do this multiplication, and that's because sometimes the denominator and the numerator of these are actually binomials or polynomials, so it gets confusing if you do it around the other part, which is why I kept erasing. So I'll multiply the top and bottom here by 5, and multiply the top and bottom here by 4. That way the denominators will both be 20. Okay, so I'm not just doing this at random, I'm purposely trying to get the same denominator. So that's 15 over 20 plus 16 over 20, which is equal to 15 plus 16 over 20. So our final answer is 31 over 20. And if either of these fractions could have been simplified, they should have been simplified. They can't be, so we're not going to. Alright, so that's just adding and subtracting fractions, something you're supposed to know from a long time ago, but just in case you forgot, this is a refresher. Let's look at some irrational numbers. So pi plus pi, hold on, let's take a look at the question. Evaluate each of the following for an exact value. Now 3.14 something something is the value of pi, and since I don't know what that is, I can't write an infinite decimal, and nobody can write the infinite decimal for pi. It makes the most sense to leave pi represented by this variable for pi. It's still a constant term, it's still a number. You wouldn't think of this as a number that changes. It's some known value, but we don't know how to write the number. So pi plus pi is like having two variables, so that would be equal to 2 pi. And just like we had mentioned, let me close up those. I'm not used to using the smartboard to write radicals, but it doesn't do the top. These are, pi and e are unlike terms, so these cannot be combined. So that is in its simplest form. And let's see. These are like terms because they have the same variables and they have these same radicands. So we can simply combine the coefficients. 2 plus 5 is 7. So this is 7 radical 5, and radical 5 cannot be simplified, so we leave it that way. Here these have unlike radicands, so these are unlike terms. But we can simplify this radical, so let's do that. So that would be 2 radical 4 times radical 2 minus 5 radical 2. 4 is equal to 2, so this is 2 times 2, which is actually 4. Radical 2 minus 5 radical 2. Now they have now they're like terms, and because they're like terms, we can combine them. So that's negative 1 radical 2, or just negative radical 2. Because again, we don't need to write a 1 if it's a 1, it's a coefficient. Alright. I kind of skipped over this, I didn't mean to. Evaluating is to calculate or determine a value of a numerical expression, which is just another way of saying simplify and get an actual number. So evaluate, you need to get a number. Simplify, it doesn't necessarily need to be a number, but it can be. Okay. Take a look here. Write the following repeating decimals as fractions. Some of these are interesting. This is actually 2/3, but how would we know that? I'll show you. You probably won't use this very much, but I like it. I think it's very cool. So if I call this x, I can say 10 times x is equal to 6.6666 forever. If that makes sense, by multiplying by 10, the decimal moves over one place. Alright, and now by subtracting these from one another, we get 6, because all of these repeating 6's cancel out, all of them, is equal to 9x. Now, if you remember how to solve for a variable, we divide both sides here by 9, and divide by 9, we get x is equal to 6 over 9, which is 2/3. And as you might have noticed before, x is also equal to 0.6666666 forever, so therefore x, this suggests that 2/3 is equal to 0.6666666. Slightly more complicated. Let me move this over here, I think. Can I move it? They're all plugged in together, so let's take that away and paste it over here so there's some more room. Alright. So this is the same kind of thing. This is equal to, let's just say it's x. I like to use x, it's easy. Now this time I'm going to move the decimal over twice. So in order to do that I have to multiply x by 100. So this is 100x is equal to 35.35 forever. So by subtracting them, we get 35. I'm going to put a subtraction symbol here. 35 is equal to 99x. So just like before, we can divide both sides by the same thing. So we'll divide them both by 99. And we get x is equal to 35/99. So that means 0.353535 is equal to 35/99. And now this is the really bizarre one, and it's really, really bizarre, and that's because this is equal to, let's say it's equal to x, this is actually equal to 1. 0.999999 is equal to 1, which no one believes, but it is. So again, we multiply both sides by, multiply this by 10, we get 9.9 forever. This is equal to 10x. If we do the subtraction, we'll get 9 is equal to 9x. Divide both sides by 9. We get x is equal to 1. So 0.99999 is the same thing as 1. And if you think about it, what would I add to 0.9999999 to get 1? I would add 0.000000, which is 0. So 0 plus 0.9999 equals 1, then 9.999 equals 1. Similarly, I can say, if I take 0.99999 away from 1, what will I get? And you'll say 0.00000, which is 0. So 0.999 is 1. So hopefully that made some sense. Yeah, this is just a neat little trick for writing these as fractions, proving why these are repeating decimals are actually rational numbers and not irrational numbers. Now you can't show that terminating decimals, terminating decimals can all be written over as, darn, I totally forgot to mention terminating decimals. Like 0.5 is equal to 5 over 10. But non-terminating, non-repeating decimals, there is no strategy to make them fractions. Otherwise they would be rational numbers. But they're not. Thank you.